sorry. So to calculate input shaft bearings, we need to know distances A, B, C. In previous class, we discussed this question, and I shown you how to find distances A, B, C. Approximately 80, 80, 32, 33, approximately. And after that we know these distances, we can calculate bearings. Okay. So to calculate bearings, we should know some parameters. Torque, it is from table 3, input torque. Rotational speed, pinion pitch angle, table 7, pitch diameter, mean diameter, like this. Also table 7. Profile angle 20 degrees. We selected gear with such angle, and cone dynamic and static load capacity of selected bearing. We selected table. We should know diameter, code, and C0 static load capacity and C dynamic load capacity. Then force diagram. It looks like here, and what we know and what we should find. If we consider this our shaft, and here we have a contact between pinion and gear. It is considered that we have contact in one point along in the middle of phase width, approximately the middle, because correctly this distance is approximately 0.4 from phase width. But to make it easier, it is considered that forces are applied in applied in a one point. So what we have? We have tangential force, tangential. Blue, it is a radial force, and this green is axial force. We know that tangential force acts on a tangent line to pitch diameter, to operating pitch diameter. Radial force is directed from point of contact to center of rotation. And we know that axial force acts along axis of shaft. But we have some distance between axial force and axis. we can calculate force, tangential force. It may be calculated like 2t divided by d. T is torque, d is dm. It is a moment. Ft 2t divided dw1 or dm1. This formula dm1. We know these two parameters, but if you calculate your gear transfer, you have this force which is calculated previously. Table 7, Ft, tangential force. So you can calculate or take it from table. Then we know value, we know direction of this force. And where it is applied. Then radial force, I said, is directed to the center of rotation, and value radial force, it is Ft tangent alpha cosine delta. Ft we know, and alpha is 20 degrees, cosine delta, it is calculated value. In your calculation, delta 1 from table 7. So we know point of application, we know direction, and we know value of this force. And third is axial force Fa, the same, Ft tangent times sine delta. Here cosine, here sine. So we have three forces. Schematically it looks like here. Radial force, tangential force, axial force. And we have one more force, it is a coupling force. This force is not force which is transferred from engine to the driven machine. This is an additional force which may be in our design according to mistakes in manufacturing, in mounting. So it is additional force. It is not force which translated from engine to pinion. So this force may be calculated according to this table. We found parameters of coupling, and we took this type jaw compression coupling, and it may be calculated like this force, and we usually take 10% from this total force. So this is a value of coupling force. But what about direction and point of application? This force is applied in the point of contact between key and shaft. This force is directed in any direction. We don't know where, what is this direction. That's why we use direction which creates the highest load for bearings. If we direct for this force at the same direction like biggest force in gear transfer, we have the maximum load on a bearings. That's why it is in the same plane and in the same direction like Ft. And finally, this force is distributed along this surface, and we need to integrate to find where is this force is applied. But to make it easier, we consider that this force is applied in the middle of a key. Who is it? So we know in such case direction, force of this force value and point of application. And finally, we have forces. We know all forces which act in our design. And you see that tangential force is perpendicular to the axial force and radial force. That's why it is better to consider separately influence of forces, action of forces Fa and Fr in one plane, and Ft and Fc in another plane. So if we consider this force at this plane, we have in this plane radial force and axial force, two forces which act in a vertical plane. And radial force creates a bending moment according to force and distance, and Fa create the moment in any place. So Fa times half of diameter times radius creates bending moment. It is a vertical plane, and if we consider horizontal one, we'll have something like this. Two forces which are directed in one direction and two forces which are reactions. So finally let's consider this diagram schematically. It looks like here. This is a pinion, axial, tangential, and radial forces. And Fc, it is a coupling force, we know its value. So, how to find reactions? You see that we have reaction in vertical AV and horizontal AH. The same BV and BH. So, total reaction RA and RB, we consider it in two components, AV and AH. In such case, we can solve this equilibrium condition for vertical plane and horizontal one. For horizontal one and the same forces in vertical. So I shown you in lecture that we can write equilibrium condition, and from this equilibrium condition we can find reactions. But to know these reactions we should calculate radial force and Fc and moment. Moment may be found like Fa dm divided by 2. Fc I shown you 50 times square from t, and distances ABC we found from diagram, from such diagram. So let's consider example. Force diagram I shown you. So tangential force from table 7, this value. Radial Ft tangent alpha 20 degrees, cosine of 90. Fa the same. Here cosine, here sine. Fc coupling force 0.1 times 50. So we have value like this. This value is very small, usually approximately 25, 45 Newton. So very small. And the bending moment, which is created by force Fa, looks like here. Then reactions. A vertical, A horizontal, B vertical, B horizontal. You see formula where we have components. It is in course project tutorial, page 89. You see A vertical, A horizontal, B vertical, B horizontal. They are here. Pay attention that you need not to calculate, with a very big number of digits. Uh, four, four, three, 4 digits enough. Then, what you should pay more attention, that sometimes forces are negative. You see here two negative results. It means that this force has direction opposite to those we selected preliminary. You see we have reactions A vertical, A horizontal, which are directed like this. But minus means that we have direction opposite. B vertical and B horizontal. And finally, A, B may be found like square root from these two components and these two components. Of course, B is greater, 3,500 Newton. Then required dynamic load capacity. First, we should know what formula we need. When we know load, by the way, when we considered and found loads, we can calculate separately for A and for B bearings. And you'll see that B reaction approximately 3 times greater than A reaction. And of course, bearings will be different. But from technological reasons, better if we make both bearings the same, with the same load capacity, with the same dimensions. Sometimes it's when, for example, airplane designs may be another solution when we calculate and select bearing for each support separately, but it saves our weight, and design will be lighter, but it is more expensive. So we will calculate according to the biggest loaded support. Second support we will take the same. So how to find it? Formula to calculate load capacity is here, and strength condition looks like here. C, it is a calculated value, should be less than catalog value. C is bearing dynamic load capacity from catalog. So it means that we should calculate required value and compare it with reliability enough load capacity. So we should know these parameters like here. Let's consider there. A1, it is reliability factor. It is normal reliability is 90%. It means that 90 bearings can work during service life without damages, and 10% may be with damages. If we need load reliability higher than normal, we should use A1 reliability factor less than 1. In such case, when A1 decreases, C increases, and we need to take bearing bigger to avoid damages. So let's take 1. Then operating condition factor A23, it is operating condition factor. It may be used for conditions usual without shift of axis with misalignments and lubricant and best material and flow of lubricant. In such case, the best conditions for bearings. So if we use ball bearings, we selected ball bearings like first approximation, and the usual condition, it should be 0708. I took it 08, but sometimes you can take 07. Then service life in millions of revolutions. It should, no, sorry. It is calculated according to this formula, and its rotational speed, and what? No, сменился. Okay. So n, it is rotational speed of input shaft. Then LH, it is your service life in hours, and divide by 10 power 6, it's million, because service life should be calculated in millions revolution. Value is relatively big. Then exponent. P small. You see, in this formula we have two letters P. P capital, P small. P capital, it is equivalent load. P small is the exponent. For ball bearings, exponent P equals 3. For roller bearings, 10 divided by 3. So, because in our case we use ball bearing, exponent is 3. If you need to change bearing from ball bearing to roller bearing, in such case you should change this 3 on 3 point, comma 3. Rotation factor for rotating shaft. It means that according to our mechanism, we have rotational movement of shaft. Just a moment. V. V is the rotation factor. If in a case when internal ring rotates, load factor, sorry, here should be factor. Correct, about load vector. When we have constant direction of load according to rotating ring of the bearing, V is 1. When external, V 1.2. In our cases, this parameter is for rotating shaft is 1. Axial load criteria, FA divided by VFR. Pay attention that FR, it is not radial force. You see here, radial force FR. This FR, they are different. FR here is a radial load on a bearing. Here it is a radial force in gearbox, in pinion contact. We have tangential force, radial, axial, coupling, and all of them all of them create load. So it means that this load FRB, it is a FR, and this is a result of summary influences of 4 forces, as minimum 4 forces on load. That's why FA, it is the axial force. It is axial force. We don't have another forces. Axial force 269. But FR, it is not radial force. It's the biggest mistake. Here should be radial load, not radial force. Radial load, the bigger one from these two loads is 3,455. Is here. That's why load criteria 7,000. Axial load factor 0.19. Why? Because for ball radial deep groove bearing, criteria E smallest is 0.19. If we have load less than 0.19, we should use X radial factor 1, y 0, e 0.19, e 0.19 is the smallest one. It means that if we use such type of bearings and load and E 0.19, it means that radial load much greater than axial. Axial is too small. We can neglect FA. So in E 0.19, load factors X and Y. X and Y. If acting bearing load factor less than E 0.19, in our case it's 700 hundredths, it means that X may be 1, and if X1, Y is 0. It means that we neglect axial force. In another case, when FA relatively big, if we compare with F radial, with radial load, and in such case it bigger than E, we should use X 0.56, Y from this table. In our cases, usually 0.19, E0.19, FA to FR less than 0.19. That's why X is 1, Y is 0. Then two coefficients, KB and KT. KB is a safety factor considering non-uniformity. For light load 1, for medium 1.3, 1.8, for heavy load 2, 3. So I took it 1.3, you can take it 1.3, 1.5, as you would like. KT, it is a temperature factor. If working temperature less than 125 degrees centigrade, in such case it equals 1. It means that bearing surface temperature should be less than 125. In our case, we should use this variant because if we use mineral oil in gearbox, better if its operating temperature will be less than 80 degrees centigrade. So it means that it is not 125. So that's why we use it 1. Temperature factor is 1. Equivalent load. According to this formula, KB, KT, we took it here. V is 1. And if we, like in my case, Y is 0, Y 0, we neglect axial force, and we have P capital, equivalent load, safety factor times radial force. But radial force, it is a radial load, it is not radial force in contact. So finally, load capacity looks like here. P is a load, equivalent load. L, this value. P is a free, it's a P small and P capital. So like this. So we have dynamic load capacity 49,000 Newton. So what we should do? First we should compare it with dynamic load capacity of catalog value. 32,000, but we need 49. It means that our bearing can't take this load. So what we should have to do? First variant, we can take another bearing. What's another bearing? Let's look at we know that we use 40, 208, 32, but we need 49. It means that 308 with 41 is not enough. We should take as minimum 408, 63. So first variant, we can increase bearing up to 408. In such case, load capacity will be enough. It's the first variant. Then we can use another bearing diameter, increase up to 45 and take medium series. In such case we have 52. It's rated at 49, so it means that it may be. But in case 408, we have the same shaft and another frame, 110. For 309, 100. So this variant increases bearing diameter on 20 millimeters, but it is less than 408. Maybe like this. One more variant. We can take another distance, B. You see here, B, 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 B. If we increase B, we decrease loads, decrease forces, reactions. B is in here and in denominator, but if we increase B, it's better. So to compare these variants, So in a tutorial you can see how it looks like. First variant 208 and B80, but this variant is not correct. Second variant, if you compare first and second, you see very big variance, 408. If we increase length, of course, if we increase the length of shaft, we increase the frame also. We increase the we decrease bearing but increase frame. It's a very interesting question to find how it depends on. And one more variant is 309. Diameter 45, distance 80, and 309. Maybe. So to answer this question, what type of solution we should have? We should compare in a drawing and solve this problem individually for each design. What variant is better? Because not only these variants, these variants are not all variants. Maybe one more variant is change type. We considered ball bearings, but let's consider tapered roller bearings. For example, if we need 40 and we have 208, 208A, A means it's high quality, the same dimension, 40 diameter, bore diameter, outside diameter 80, the same like for bearings, ball bearings, but load capacity 46, 58. So if we use this bearing, we have load capacity enough for our case. So it means that we can change type of bearing. We can use tapered roller bearing instead of ball deep groove. In such case, we have the same dimensions but another type. Another type means that you should recalculate load, and you'll see that we have one more safety safety part of load for these bearings. We need 49, but if you calculate for radial bearing, you'll have this load less than 49 because exponent will be 3,33. I shown you. Exponent for ball bearing 3, for roller bearings it's 3,33, and we'll have high load capacity. So it's also maybe correct solution for your design. Finally, when you calculate and you select your variant, you should show it to me, and we solve this question how to solve this problem. So in my case, I took final bearing code 309. I told you about this solution, and we can continue next. But first, to continue next work with design, you should finish with these calculations. So finally, I put this class in YouTube, of course, but I would like to see your results. We calculated kinematic calculations, gear transfer, selected elements, and now we add bearing calculation, but I don't see your results. Please show me what you have. Okay. So do you have any question? No question. Okay. So I stop screen. So okay, if you know questions, that's all today. I'm waiting for your results. Please